I have started the recording. Okay, I think we'll start. Is there any question from what was discussed previously so far? Of course, we concluded our discussions on identity management, and today we'll start a new topic, which is interoperability. But if there is any quick question, I can answer. Okay, so if there is no question, let us make a couple of announcements. First of all, of course, as I have circulated over email, we'll have a quiz at the start of our class on Friday, and that would be on identity management. The second part, second announcement is about the third class test, which we had previously announced to be held on 19th of October, but we noticed that 19th is a holiday. So what we have decided is that instead of holding it on in that week, we'll hold it on the previous week, that is on 12th of October. So Friday, the 12th of October will be our third class test at the usual class hours from between 9 to 11. We'll of course send an email once again, but it is just a heads up for you. And we'll continue with our usual tutorial and assignments during the Friday classes. And also we'll have, besides this Friday's quiz, some more quizzes which we'll organize in the coming weeks, on Fridays, of course. So that is what I thought of announcing at the start of the class. Now let us get started with the new topic, which is blockchain interoperability. So this is just a starting slide, which we all know about. There are two types of blockchains: public or open permissionless blockchain, private closed permission blockchains. Now, although there are broadly these two types, within each type also there are several possible chains. And we'll see that as we look at various applications, so these applications have developed over the years. Sometimes these are spearheaded by different companies and enterprises, where there are blockchains that are specific to uh, different such even business verticals. We'll look at that one. While we are talking about blockchain in the context of our country, there is also a lot of initiative uh, by the government, and of course, there are participants from the industry as well. Now, the government of India, under the aegis of Ministry of Electronics and Information Technology, MeitY in short, so they typically handle these types of requirements as to develop a national strategy on blockchain. So they are one of the arms is the CDAC, and there are other also organizations within the ministry and the Department of IT. So they came up with a national strategy on blockchain. So if you get time, you can take a quick look at this particular document, which is also linked here. And I mean, this is just a 28-page document, including all these TOCs and all. And it's something that will give you some idea about the initiatives taken by our own government in this blockchain space. And they have tried to take into consideration the technology aspects, as well as the considerations of the other stakeholders, including various businesses and users, so how they can interoperate. And they also talk about how these different types of permission and permissionless blockchains, public and private, they are organized and so on. So a lot of these are actually already covered in our lectures, and this will give you a good idea about the nationwide initiatives. So you can take a look at it at a time of your convenience. Now, more importantly, if we look at this diagram on our right, so which is about national blockchain distributed infrastructure. So there is this overall grand plan that will have these types of different regional nodes, and then we have this layered architecture where we have chain layer where these are shared ledgers, and which could be for property. Like there is a lot of work in the area of applications of blockchain in property registration, land registration, and so on, which is a typical application where generally there is nothing that much confidential. Like who owns the property, one can also go to the appropriate registry and get it by taking maybe paying a small fee, and then get a full history of the transfer of property, sometimes called search report, and so on. So, because these are not that much confidential, at least not the entire content of it, so this could be easily handled in public blockchains. Similarly, for education also, and to give you some idea, and you can see in the same diagram on the top right, you have this notion of DigiLocker. So, if you have seen that, say for example, DigiLocker by the boards, and which can be actually used and presented, which we had discussed in our last topics of presenting our credentials. So these can be actually linked with this education chain, and similarly for insurance and so on. And then there are these different platforms like Hyperledger, Fabric, Sawtooth, Corda, and other platforms. And then smart contract, there are domain specific smart contract layer or design patterns for smart contracts. Then in asset layer, there is this creation of asset, transfer of ownership, and then tracking of assets. And then we have, more importantly, the cross application access layer, where this notion of interoperability comes, where we have to have certain levels of access across multiple blockchains. And on the top, there are critical national level applications like finance, governance, health, smart city, insurance, and so on. And of course, there are different types of value added services like proof of existence, proof of storage, and so on. And some of these are also mentioned in that this document, as I showed. And on top of all these, there could be some analytics done, and maybe using some machine learning techniques, one can come up with some sort of predictions. There are need for integration with existing services, as I said, this Aadhaar and DigiLocker and so on. And of course, connecting all these, there is a security vertical that talks about identity, privacy, authentication, authorization, and access control, and so on. So overall, this is an architecture, and which we are showing here to motivate that indeed there is a great need for interoperability across multiple different blockchain networks. Now, this is again a very quick glimpse of the various types of blockchains that we have, of course, starting with Bitcoin and Ethereum, and then there are, say, hundreds of such possible blockchains which are there. And on the right-hand side, also, we show the private or closed permissioned blockchains like Hyperledger, Corda, and so on. Now, what is happening is that whenever we talk about interoperability, we have to understand that this notion of interoperability for permissionless blockchains and for permission blockchains, there is some difference. Essentially, if we consider permissionless blockchains, which are mostly cryptocurrency driven, like you of course have Bitcoin and Ethereum, this Ether and others. Now, So there, when we talk about interoperability, it is more about transferring of assets. So typically, we'll see very quickly in the following slides that it is about transferring, say, one cryptocurrency from one blockchain to an equivalent value of cryptocurrency in another blockchain. So this is more about transferring the so-called assets, and it's cryptocurrency driven. So it is quite important that we ensure that these are like atomic transfers, so that no party can back out, or it should not be a case because it involves money, that there should not be a situation where one party, I mean, two parties agree to exchange some coins, and then one party ends up getting both, the other does not get any. So we have to consider those issues which are more important for such cryptocurrency driven interoperability. In contrast, in permission blockchain, it is more about data transfer. That say we have one blockchain, as just to give you a simple example, suppose there is a blockchain of for the boards. Okay, so they keep all the data about our board exams. Or say there is say we have, for instance, say a blockchain where we have these JE advanced or gate results is are published. Now if these are published, and then when it comes to admission, then that say the IIT system has some admission procedure for gate. So there is a common admission, or for JE also we have common admission procedure. So one part of that is the exam part. So if you see that the exams like JE main are conducted by one organization, and JE advanced is organized by another organization, and then there is a need to transfer data from one such party to another. And if these are being maintained on blockchains, then what is important is that a consensus view of data should be transferred from one such chain to another. So when you talk about interoperability in these types of blockchains, the permission blockchains, like the example I gave, so here it is more important. It is not about a transfer of any cryptocurrency and atomicity. That is not of that much importance. Rather, what is important is that whatever, say, the IIT admission, the joint IIT admission process would get, if that is maintained on a blockchain, from the exam related blockchain, is the consensus view of the data, that all the data that are published there, that those are all final, and there is not going to be changes. And if for some reason there is a change, so that should get accordingly propagated. And if it is propagated from one chain to another, it is very important that the data that is being transferred from the source to the destination, so both the parties understand that this is a consensus view of the data. And of course, maybe the example that I gave, that typically would be relatively static once the data is passed on from one chain to another. But there are many other situations, as we'll see when we talk more in more detail about permission blockchains, where it is about the example that was taken in one of our first few lectures about supply chain blockchain. So there, this need not be part of one single blockchain. So part of this could be, with the finance part of it, like how the payments are made, how the banks will ensure that after supply of material, the payment will indeed be released. The other part is about shipping. Part of it could be import, export, and so on. So each of these might be actually running on some specialized blockchains, and there is indeed a great need for transfer of data, and that data will always be changing, because the status of a shipment can change from time to time. That particular ship has reached a particular port, and it is expected within so many days, and accordingly certain things would be arranged. So all these will have to ensure that a consensus driven interoperability can be actually ensured for permission blockchains. So what we'll do is that we'll talk about some techniques for public blockchains interoperability, and also some for permission blockchains. So, so first we'll look into permissionless blockchains, the public blockchains. So what is found is that when we talk about these individual public blockchains, like say we have Bitcoin, we have say Ethereum and so on. So they are and they have been developed and they are still getting developed, and new such public blockchains are getting created. So they are operating as isolated silos. So uh, uh, there is no relationship as such, of course, between Bitcoin and Ethereum. And it is not only for these two, but which apparently are quite different. But even if there are some variations over the basic concepts of Bitcoin, and there are other similar networks, but they also do not tend to have any such link and cannot directly operate with each other. And that's why we are saying they are more like isolated such systems. So they enable secure and trustless currency transaction between parties, and but they are within the same network. And of course, there are, as mentioned, there are several such cryptocurrencies which are in operation. And of course, that most of these blockchain networks, they have their different protocols and standards, and they have their own cryptocurrencies. And that's why they are going to operate and they continue to operate in complete isolation from one another. But we'll see very soon that there indeed is a requirement for interoperability among these permissionless blockchains, the public blockchains. And there is a reference that you see here, which is one of the papers we'll discuss, but not exactly now. So first we'll talk about two basic approaches, and after we have our discussion on the security aspects of blockchains, then we'll come back and discuss about this particular paper, because this is about interoperability, but it also addresses some security issues. So once we have understood the security concerns of blockchains, then you will be able to appreciate it better. So this particular paper, which is on this slide, as you can see at the bottom, so that is the one we will cover later when we come back. Now, of course, these are some examples of so many different types of blockchains which are operating in isolation. So let us now motivate about what is meant by this interoperability or cross-chain uh, uh, operations in the first place. Now, what is an operation in this context? So if you see that if you're talking about cryptocurrencies, and we have this one cryptocurrency network on the left, say Bitcoin, and one on the right, say Ethereum. Now, if you see that this example, so which we have to understand what are the different possibilities. One is that Alice is part of the Bitcoin network and also part of the Ethereum network. So it is the same person, Alice, and Alice has one Bitcoin, wants to transfer one Bitcoin from her Bitcoin, from the Bitcoin network in which she is a member, to the Ethereum network in which also she is a member, and say the current rate of conversion is 1 BTC is equal to 33 ethers. So what Alice would like to do is that Alice would like to, as you see in the title of this slide, that Alice would like to transfer her asset, that is one Bitcoin, from one network to another. So this is like a cross-chain asset transfer. Now, of course, this is an example where we have same person Alice, member of both the networks. So instead, also it could be that the transfer needs to be done between different accounts and holders also. For example, Alice may want to transfer one Bitcoin from our Bitcoin network to Bob, but Bob would be paid in equivalent number of ethers. So, of course, in the first case, when Alice was transferring to herself, so if it did not get transferred for some reason, it would be there with her. But for this case, when it is transferred to another person, then it's important that it is done in a way that if something goes wrong, Alice will be able to recover her money. So now this is a typical example of cross-chain asset transfer, which is of importance for such permissionless public blockchains. Now, how can this possibly be done? So you see in this example, Alice is a member of the Bitcoin network, and Bob is a member of the Ethereum network. So one possibility is that for doing this transfer, Alice uses a third party uh, who owns greater than 33 ether. So what Alice could possibly do is that this third party who will have accounts, say, in both Bitcoin network and the Ethereum network, and Alice would transfer to this trusted third party that 1 Bitcoin, and this third party will then transfer the equivalent number of ethers to Bob. So this is one possibility, like an exchange which can take the money from Alice and then convert it into the target cryptocurrency and then make the payment to Bob. Now, this is definitely a possibility. So, as is shown here, that trusted third party, which we showed there in an abstract sense, would indeed be a member of both the Bitcoin network and also of the Ethereum network. And as is shown here, Alice transfers 1 Bitcoin to this TTP, and TTP then sends 33 ethers to Bob. Now, this is a fairly straightforward solution, but it has got a number of issues. First of all, this transfer from Alice to this TTP, so that is taking place, say, at some time instance at T0. Now, this TTP will transfer the money to Bob up at some point of time T1. So there might be some gap between T0 and T1, and which could be significant. Now, this is something which is equivalent to, for example, if we want to pay for a conference registration fee in dollar, then they have a bank account. So what we do is that if I have to transfer $100, my bank can say that, oh, you have to deposit with an exchange rate of 75 rupees. That 7,500 you deposit with us, and also some processing fee, maybe another couple of hundred rupees, and this total of 7,800 is what you pay to the bank. And then what they will do is that at that exchange rate of 75 rupees per dollar, so they will now transfer $100 to the bank account of the conference. But this process itself can take quite a bit of time, because it can go to the my bank, some negotiating bank, maybe in another city in India, and then it will talk to the corresponding bank of the conference, which of course need not be and is not likely to be the same bank as where I am having my account. So they will also have to negotiate this, and finally it will go to that bank, and then it will end up in your account. So of course we have these all these concepts nowadays with Swift code and all, so that it can be uniquely tracked and can trace what the money is currently. But it takes some time to do those things. And also remember that we are considering these as trusted parties. So the bank is a trusted party, just yet another node in the network, and they are as much trusted as untrusted about any other node in the network. So it is just that maybe they have the reputation and you would be able to willing to transfer through them. But then there are these are the so-called centralized crypto exchanges, and uh, but they are at the once you have initiated the fund transfer, then its fate is now at the sole control of the exchange administrator. So typically it is fast. Once it is done, the transfer is often very fast. It depends on how quickly that can do the transfer. But there is a lack of security. If there is an attacker who is targeting the exchange, then there could be a chance that there will be theft from the centralized exchange. And also what can happen is that if that exchange shuts down, and say there is a delay, we are talking about in milliseconds, but it could take some more time. And in between, if there is an issue like this, one particular exchange had shut down, and then that can lead to loss of bitcoins. And there are several instances where there could be these difficulties that the senders, say Alice and Bob, are facing because of depending too much on the trusted third party. So there are these some more links here, as you can see on the slide. So you can take a look at those to get more details about these issues. So essentially, the summary is that depending on these trusted third parties is always not going to be um, very interesting and very secure. And I said interesting because all said and done, we computer scientists are always trying to find fault with simple solutions and then come up with more complex solutions and then show that they are really good. So with that idea, people came up with different such algorithms, as you say, or protocols rather, for transfer of interoperability among these permissionless blockchains, and they show how such asset transfer can be done. So first, I show this example that we are now talking here about asset exchange. So if you see, we have uh, a Bob here. So in the previous example, we had Alice as member of Bitcoin network and Bob as member of Ethereum network. And then we had this trusted third party, which was a member of both the networks. And Alice could transfer one BTC to that, and then that TTP would transfer 33 Ethers to Bob. Now, here what we are saying is that here we have Alice and Bob both in the Bitcoin network as well as in the Ethereum network. So Alice, now you see the requirement is that Alice is going to transfer one Bitcoin to herself. Okay, and that will go there in the Ethereum network as an equivalent of say 33 Ethers. So instead of having a trusted third party, a centralized such exchange, as we mentioned, because of the centralized nature of these exchanges, there are certain security issues. So instead, what we have is that another entity, Bob, is going to and Bob will transfer 33 ethers to Alice. So it should not be a case that Bob gets this one Bitcoin in the Bitcoin network and then can get away with by not paying 33 ethers to Alice in the Ethereum network. Okay. So, I mean, assuming that we are originating it from Bitcoin, or it would be the other way. So Bob could transfer 33 ethers to Alice and then expect to get back one Bitcoin from Alice in the Bitcoin network. So both of them should be done in an atomic manner. So the problem is that without the presence of any escrow is basically you can consider a financial institute or an entity rather, who is controlling the fund for some time. So they are getting the money from one side and they are transferring to the other. And in case of any dispute, you can have to some extent you can take it to the this escrow entity, who can then figure out what is the status of the fund and so on. So, if of course here there is nothing like that, no entity that is going to take such a responsibility, and we are doing it in a decentralized manner. So the funds are in control of the sender and receiver parties. It is quite possible that one party might abort the exchange after receiving the funds. So they got the, like in this previous example, Bob got the money from Alice, say one Bitcoin, and then Bob decides to quit. Okay, so it is to be ensured that whatever protocol we use, that is going to end up in making it atomic, so that if Bob tries to get away with that one Bitcoin from Alice and not paying her 33 ethers, then that is not something that would be possible. So Alice should get back or should be refunded her one Bitcoin. So there could be synchronization problems between the two networks as well as the sender and the receiver. And definitely there is need for some agreement on the exchange rates and whether one Bitcoin is 33 ethers or 34 ethers and so on. So that needs to be kept in mind, and maybe all the transfers should take place within a very short window so that the exchange rate fluctuations will not have a major impact. So these are some of the considerations, and especially when we are talking about asset transfer in the context of such permissionless public blockchains. And as we'll see later, that when it is about data transfer between permission blockchains, this of course is not that much of a concern, because there we are not talking about exchange of cryptocurrencies. Is there any question up to this? So if
No,
we
sir.
Okay, thanks. Yeah, you can always ask me later also. So, if we see that if we consider such cross-chain asset transfer, using atomic exchange. So it is like Jack is acting like an exchanger. Then this part about atomicity is that this synchronization, and then one party, if it aborts, then it should be ensured that the money is refunded. So if you see in this example, we have Alice here who wants to make a payment to Bob. So Alice is sending the money to Jack, the exchanger, and Jack is sending uh, 33 ethers to Alice. So in the first network, Alice is sending 1 BTC to Jack, and Jack in the second network is paying 33 ethers to Alice. So then these two, that 1 and 2, they should take place atomically. That if Jack gets 1 BTC from Alice, it is important that it is ensured that Alice gets these 33 ethers from Jack in the second network. And once this money has been transferred from Alice's Bitcoin network to her account in Bitcoin network to her account in the Ethereum network, so she has got those 33 ethers, and then of course she can make the payment of 33 ethers to Bob eventually. So what is important is that this 1 and 2 as marked here in the figure, so this should take place as an atomic exchange. That is the first thing. And then the main challenge here is to solve this problem of atomic exchange, because if that can be solved, then transferring from Alice to Bob, as we see here, that is more straightforward, and Alice can do it at any time. So we'll see that how actually this cross-chain asset transfer using atomic exchange can take place. So we'll study this particular paper, which was published in the Principles of Distributed Computing Conference, and which is one of the earliest work in this topic. So what it does is, it is a very important, not only important, it's an interesting paper, and it's an easy to read paper. So we'll mention which particular sections of the paper you need to read. It is most of the first few sections, and which are very easy to understand also. So what it says is that atomicity, of course, is that defined in terms of an atomic transaction, which is an indivisible series of operations, such that, of course, either all occur or none occur. So it is very straightforward definition of atomicity. So what it ensures is that there are these cross-chain swaps. So swapping of assets, and we'll see that first we'll talk about, say, swapping of cryptocurrencies, Bitcoin and Ethereum, but later on we'll see that there could be swapping of other types of assets in one of the examples. So it is not always cryptocurrencies, and we'll see in that example it is a combination of cryptocurrencies and other physical assets, but of course those are to be maintained on the chain. We'll look into that. So an atomic swap protocol would guarantee that if all parties conform to the protocol, then all swaps do take place. So, so it is important that if we follow the protocol, then the swaps will indeed take place, and there would not be any issue. Also, if some parties deviate from the protocol, so say there are, say, 3 parties which are involved in it, and if one of them deviates, then but the other 2 conform to this. So we have parties, say A, B, and C. So if Alice is, so A is Alice and Bob and Carol. So if Alice, Bob, and Carol, if all of them conform to the protocol, then the swaps will take place. But if, say, Alice deviates from the protocol, but Bob and Carol, they conform, then the deviation of Alice from the protocol should not let or make Bob and Carol worse off. So either they gain, or they do not have any impact. And there is no coalition that can be formed between some of the parties together that would have given them an incentive to deviate from the protocol. So deviation from the protocol is not going to help any one of the parties who are going to deviate. And those who are not going to deviate, they will not be worse off. So we'll see that these interesting guarantees are how they are ensured in this particular protocol that was proposed. So let us see that the initial goal is that, if you see at the top, that Alice will transfer 1 Bitcoin to Bob, and Bob will transfer 33 ethers to Alice. Now, how is this done? Overall, the idea is like this, that uh, there will be smart contracts that would be initiated at both the ends in the 2 networks. And this is the most important and interesting part, is that there would be a common spending condition such that when the condition is met, both the parties would be paid simultaneously. So that means that when that condition occurs, then it cannot be prevented that one party gets the payment and the other party does not get the payment. So the idea is that is to define the condition that needs to be met in such a way that as soon as that condition is met, it will be letting both the parties get their payment. So Bob will get his 1 BTC and Alice will get his 33 ethers. So how is it done? So if you see that simple example, that Alice would publish a contract in Bitcoin network. So contract say A, which says that it would pay 1 BTC to someone who will be able to meet that condition. And Bob would create a contract in the Ethereum network that would say that when this is done, then the 33 ethers would be paid. So when this common trigger actually occurs, so this contract A, which Alice had created, that would make that payment of 1 Bitcoin to Bob. And then when this contract B is, because the same common trigger, common event to trigger contract B also to get the payment of 33 ethers. So if we talk about such types of contracts, so you can think in simpler terms, where of course the contracts can have more little coding. But if you look back to our discussions on how those scripts were executed when, say, Alice was making a payment to Bob and so on. So what we said, we had these simple scripts also where we had this possibility that one could say that if this time at this time this payment will be released, right? So that is what we had seen one example. And when the script was getting executed, so it was noticed that if the time was still not the time till which the funds were frozen, so then this would return false when we are using the stack based processing, and then the further other components of the scripts would not get executed. So that meant that that was typically a condition when the which needs to be met in order for the fund to be transferred. So if we simply consider that to be a common trigger, so we could say that the Alice makes this contract which says that Bob will get the money at say 10 a.m. on 21st of October 2021, and also Bob gets creates a contract which says Alice will get 33 ethers at 10 a.m. of 21st of October 2021. So that would mean that the common trigger in that case would be that particular time instant arriving, which is, as I mentioned, 10 a.m. on 21st October 2021. So both Bob will get the money based on the first contract from Alice, and Alice would get the money from Bob's contract that was created. So you can take that as a simple example of a common event trigger, which is just that particular instant of time coming. And also, as it happens that the contracts then at the same time Bob also can claim those or that 1 BTC, and Alice can also claim her 33 ethers. So this is one typical example, and as we'll see that there are more such interesting ways of handling it, and these are what are called hash lock based and time lock based. So time lock is the one that I said that time lock means that the fund transfer is is locked till the occurrence of a particular instant of time, which is what I just now explained. So that is the notion of time lock. And instead of a specific time, what could be done also is that the block height. So if this contract is published in say block number say 1000, then it could be that another 10 blocks are to be added, then only the money can be spent. So something like that, which could block height could act as a replacement for a clock time. The hash lock is interesting. Hash lock is that uh, in order to be able to spend the fund, and if you remember that the spending fund, etc., it was all about Alice making the payment. Was like Alice would encrypt her transaction using the public. It will be paid to the the hash of the public key of say Bob, and then it will be signed with Alice's key. And then when Bob could actually use it, it was basically Bob had to claim it by using script pub key. So Alice would use script pub key to make the payment to Bob, and then Bob would be able to actually claim that amount and then pay it to somebody else or to himself by using script C. So there we saw that there are different ways of ensuring that the whatever power this particular language had. So using that, we had different types of interesting scripts that could be generated. So one of that is like using of a hash lock, where what will be done is that this can be claimed, the money can be claimed uh, uh, in this way, that this entire transaction will use a hash of a message. Okay, so there is a message M, then H of M, that is the digest of that. So that would be used to uh, it would be included in the payment, and this can be unlocked. So the script will be able to unlock only when the original message M is known. So instead of calling it as message and a digest, which is more pertinent in the context of actually creating hashes of messages, so it is the pre-image and the hash. We call this as pre-image. So X is the pre-image and it's hash HX. Okay, so so this hash lock will be enabled only when the pre-image is known. So what is done is that this the pre-image, the secret, when it is revealed, then the fund will get released. So that means that, say, Alice wants to make a payment to Bob. So what Alice can do is that she will choose some X and use HX in the script for claiming this particular fund. Now, for claiming the fund, Bob will not be able to do it using HX, but Bob will have to use X to make the claim. And what Alice would do, that when certain conditions are met, Alice will make that X known to Bob, and as soon as that is known to Bob, then Bob would be able to make the claim on that payment that was made by Alice. And also, if there are many other such transactions, contracts which are created, which were such that when X was revealed, all those claims can be made. So that means that if Alice makes this X public, then not only Bob, so if there are more other such payments that Alice had possibly made using that X, or say based on Alice's that HX, now Bob made another payment to Carol, which also used HX, because Bob does not know X. Bob knows HX, which was used by Alice, and Bob can use that HX to make some payment to Carol, and Carol can use that HX to make a payment to Amit, and so on. So the moment that Alice reveals the X, then all of them, including Bob, Carol, and Amit, everybody would be able to claim their payment. So that is the whole idea, that when the secret is revealed, the funds are released. Okay, so it is not only that one such fund that would be released. So the same HX can be used in such sequence, and actual claim or the spending of the fund can be done when this X is revealed by Alice. So we'll see that that is exactly what is used in this protocol. So hash lock, as I was saying, is type of an encumbrance, means that it is locked for some time and then somebody is claiming, that restricts the spending of an output until a specified secret key is publicly revealed. So inherent property is that once any hash lock is opened publicly, any other hash lock secured using the same key can also be opened. So it is like that the funds are locked using this hash of pre-image, and that is what will be unlocked when the secret key is publicly revealed. So for example, Alice can generate initially a secret key, say I love strawberries, and computes the crypto hash of it, which is something like this. Then now Alice initiates a hash locked contract. So this is a contract that is locked with the hash of 1 BTC, and that is the condition that if key is revealed, pay Bob with 1 BTC. So of course that means that as soon as this amount is this secret key I love strawberries is released, then this can be paid to Bob. So of course the contract also contains a hash, and then any miner can verify the revealed key. So it is not that, oh, I got it and now I am claiming it. So of course all these will go into transactions that can be verified, and then into blocks. Everything should be verified. So it is important that anyone will be able to, in the network, will be able to check that indeed what Bob is now claiming is true, because hash of that I love strawberries would match with the hash that is already there in the contract. So this is the notion of hash locks. And time locks is something, as I mentioned, that it is restricting spending or transfer of some currency until a specified future time, and instead of block time, it could be block height. And as an example, concrete example, Alice generates a time-locked contract with 1 Bitcoin, and time is 2 delta, where delta is some unit. So that means after time 2 delta, 1 Bitcoin will be transferred to the target account. So this is fairly simple. And then this target account itself could be Alice's own account. As you'll see that there is an importance of this, that after a certain time, if nothing happens, then Alice can get back the money also. So sometimes we'll use the target account when you're using time locks to be Alice's own account, or it could be even the example I gave, Alice transferring money to Bob with a 2 delta time, that when the 2 delta time has expired, then Bob will be able to make the claim. So finally, what we will talk about is this hashed time lock. So it uses both hash lock as well as time lock. So here, this example, as you can see, that Alice is spending, say, is issuing a contract of 1 Bitcoin with that hash, as we had seen in the previous slide, and then it also has a timeout of 2 delta. So the contract is such, it's developed in this way that once the key is revealed, then what Bob will be able to do is that Bob will be able to now claim that 1 Bitcoin. But then, if the key is not revealed, or even if the key is revealed for some reason, Bob has not made the claim, and if the timeout occurs, that means 2 delta time has passed since Alice created the contract, then this money will go back to Alice. So as we said in the previous example, that this money can, the last point, the target account can be Alice's own account, which is what we are using here, that with this timeout of 2 delta, the target account would be Alice. So either Bob would be able to claim it with the key if it is revealed, and get that 1 Bitcoin, or if for example, the key is not revealed by Alice in the first place for some reason, then after time 2 delta, it will go back to Alice. Otherwise, you see that these are all going as transactions in the network, and then otherwise Alice cannot claim back those Bitcoins. So for example, it could be like Bob is supposed to provide a service to Alice. Okay, so Alice, what she does is that so Bob will sell a laptop to Alice. Okay, so so Bob said, you pay me 1 Bitcoin, I'll give you the laptop. So Alice creates a contract of 1 Bitcoin, and there is this hash, etc., that are used, and then Bob can verify the transaction and knows that indeed Alice has created a contract with 1 Bitcoin payment to him, uh, but it will need this particular key to be revealed. So Bob is confident, and if this particular transaction has gone into several blocks deep, that means that Alice cannot later on retract this contract. So Bob is sure that if he makes the transfer, and if there is, sorry, if Bob can send the laptop, then if Alice reveals the key, then of course Bob will get that 1 Bitcoin. So what happens is that uh, Bob sends a laptop, and he has a proof that he has made that he has sent the laptop. And then once Alice has got it and is satisfied with this laptop, she will reveal the key, and then Alice will get his Bitcoin. But of course, if say Alice has put the contract, but Bob does not send the laptop, then after timeout of 2 delta, Alice will get back her Bitcoin. Of course, that the off-chain part, that transfer of this laptop, so Bob will definitely have some proof that he had sent it, or just received by Alice, and so on. So it should not be like this off-chain processing. We, in this example, we are not considering that. It is about uh, that Alice gets the laptop and then does not reveal the key. So that would be something that has to be handled off chain. But we'll see that when even this transfer itself is happening on chain, then how everything can be tied up together. But I gave this example of laptop, etc., for helping you to understand why there could be a need for setting up the timeout also. If one of the parties do not live up to what was supposed to be done, then the other party also should be able to get back the money. So uh, that is where we have so far introduced the basic concepts between this about this hash lock, time lock, and these hash time lock contracts, and explained what is the importance of this timeout also. And then what we'll do is that next our we'll discuss about how this HTLC, this hash time lock itself, is used for carrying out the atomic swap. So in this case, we have not yet talked anything about swapping. It is just that Alice is making a payment to Bob, and and it is all the payment will be released only based on revealing of this key, or it will be timing out, and then Alice will be getting back her money. So what will take up, so tomorrow we'll start this topic, that how this HTLC can be used for atomic swap actually. And first we'll talk about this atomic swap between two parties, and then we'll extend it to three parties. So that is what is our next topic. So we do not have time to complete the discussion, and it would be good not to start it today. So we'll stop here. But if there is any question up to this, any doubts, I can clarify, because tomorrow then we will make use of these concepts that we discussed today. Is there any question? Okay, so if there is no question, then I am stopping the recording first.